I want to thank you for being here for our last seminar of the year. Today, the Atom Seminar has the great pleasure of welcoming Professor Fernando Escobedo. Professor Escobedo received a bachelor's degree in chemical engineering from the University of San Agustin in Peru and worked for 5 years as an R&D engineer in a Peruvian company before going to the US for graduate studies. He received a chemical engineering master's degree from the University of Nebraska-Lincoln and a PhD from the University of Wisconsin-Madison. He joined the faculty of Cornell University at the end of 1998, and he received the Camille and Henry Dreyfus Foundation New Faculty Award, the Career Award for the National Science Foundation, and the Alfred Sloan Foundation Fellowship. He also won an award for teaching excellence from the College of Engineering, and currently he holds a Marjorie Hart Chair of Engineering. Professor Escobedo's research group is at the forefront of novel methodologies for the simulation of both thermodynamic data and kinetic information, from molecular level models to complex materials. His current research interests center on establishing structure, property, and relationships for materials made from customizable nanoscale building blocks such as oligomers, polymers, and nanoparticles. So once again, welcome Professor Fernando Escobedo. Thank you so much for being here with us today, and please feel free to start your presentation.
Thank you, Larissa, a lot for this kind of introduction. I need to share my... So can you see it well?
Yes.
Great. Thanks a lot for this kind invitation to present at this Atom Seminar series. It's a pleasure to sort of share some of our work on trying to engineer this polymer photoresists and electroactive membranes. An alternative title for my presentation is the pre-show to the Brazil-Serbia soccer game. But anyways, this is a work that was done by my two students, Prajwal and Yang San. So in our group, we are interested in basically trying to bridge the atomistic to the mesoscale behavior in different kinds of materials. And we are known to develop a number of methods to compute such things as free energies, transition barriers, order parameters. And oftentimes we apply some of these methods to study some interesting materials, such as, for example, different kinds of nanoparticles or colloidal systems. And in fact, we work extensively in this area of self-assembly engineering. And in fact, in my previous presentation at Atoms, I basically showed some results from this area. But for this presentation, I've chosen to basically focus on two applications that deal with organic materials, which are the ones which I'm highlighting right now. So basically, this involves two different systems. The first on engineering extreme UV photoresists, and then engineering dual conductor materials. These two systems are similar in that both involve polymers and salts, but the salts provide sort of the key functionality to the material. And so the first topic will be relatively short because that represents basically 1 year worth of our research. It's a new basically avenue. And so let's spend more time on the dual conductor materials. But in both cases, I'll give you first an introduction, then tell you about some of the methods we use, and then give you some results for the key properties we want to target. In the first case is the dispersibility of components, and the second case is the ionic conductivity. And then I will basically conclude. So for the first part, it's the idea of engineering photoresists. So as you know, Moore's law has made this prediction that the number of transistors on microchips sort of doubles every 2 years. And in fact, this huge improvement in this technology has really allowed much of the commodities of our of the present day. The idea that we could go from supercomputers that used to occupy a whole room to something that fits in our hands is really mind-boggling. And so it's expected that if this were to continue, this is really the driving force behind technological and social changes and economic growth. But it's been found that in the recent years, we are not quite doubling the capacity of these microchips, because we're kind of reaching this sort of limit, physical limit, in what can be done. Basically, how small can you pattern these microchips? So, and one of the sort of candidates for technologies to allow us to do that, that could potentially be like this new revolution in microchip technology, is the use of extreme ultraviolet radiation as a tool. So now the extreme means that you are using relatively small wavelengths for these arrays, which will be compatible with creating these sub 10 nanometer feature sizes. But we're reaching sort of this length scale almost close to X-rays. But there are tools that people are using to do this. And there have been a number of studies trying to understand how that this will work. And on the side of modeling, this involves usually a multi-scale approach from quantum mechanics to finite elements. But most of the work, or all of it, I would say, has focused really on what happens to the system after it's exposed to this UV light. And what we wanted to do was basically focus on what happens before that, because there was clearly something missing there. So just to remind you that, so the way how these things are made is that you first mix components in a good solvent, then you spin coated into a substrate, then you evaporate the solvent, and you end up with basically the polymer base. There are two key components to this material. One is the polymer itself, and then you have this photoacid generator or PAG. So we'll just be calling it PAG, which is a key ingredient in the way how this is going to be processed, that we'll show you in a moment. So the idea is that if you take this film of this photoresist, and then you expose it using this very precise tool, the UV, then what it does is basically it's going to decompose or activate these PAGs, this photoacid generator. So it creates a number of free radicals, and then eventually it creates acid. And the acid is going to react with some of the polymer. So it's basically going to compose it, so that once you apply a developer, which is an aqueous-based solvent, this solvent is going to dissolve the parts that were exposed and leave more or less untouched the parts that were not exposed. You can create these very nice features. And of course, it's really in those features that you will continue the processing to create these microchips. But the idea is that we want to make these features very small, sub 10 nanometers. The problem is that for a long time, it has been recognized that these tags, which are really salts, ionic salts, are likely not that uniformly dispersed in the material. But more likely, they're having some degree of clustering. There was some experimental evidence that this is the case. And that if you were to follow the same process, then at the end, your patterns will have this sort of edge roughness that can be very significant. Now, years before, when the feature sizes were of the order of 50 nanometers, 100 nanometers, this small heterogeneities of order, a couple of nanometers, were probably not significant. But nowadays it is, given that we want these feature sizes to be much smaller. So our work wanted to concentrate on, so what happens on the system pre-exposure. And I'll basically follow these three guiding questions to go along with our research. So the first question is, what class of material to use for this? And so for this, we basically choose the polymer base and the PAG that are basically in some standards that are used in the industry. And this information was provided by researchers at Intel. And so basically, the polymer base consists of two kinds of polymers. One of them is this polyhydroxy styrene. I will just refer to it as PHS. Another one is the polyterbutyl methacrylate. I will just refer to it as PTBMA. And so importantly, you see that you have this butyl group in the PTBMA. And so when you activate the acid is going to attack, basically deprotect this, this polymer. And this is what allows basically this polymer to be decomposed and then be dissolved by the solvent when you develop it. So, but these are the two main chemistries. And for example, the PHS is known to be so much good for dispersing the salt in the system. And so as far as, importantly, in the realistic resist that people use, they use a random copolymer of these two materials. If you were to use polymers of these blocks as sort of blends or just block copolymers, chemically they have some slight incompatibility. So a positive Florey's high parameter, and then that will lead to some segregation that wouldn't be effective. That's why they try to use this random copolymer. Now, as far as the PAC, the generator, so what they use not for the cation is triphenylsulfonium or TPS, and for the anion they use this triflate. And there are reasons why they use these chemistries, but it's not the only ones they use, but they are certainly quite representative of what they use in current research in applications. So we're going to use basically these chemistries as basis. So now I want to extend this into some of the methodologies that we want to use. So given that you need to have this atomistic detail, you have to use basically all atom force fields to do this. And now in the real system, the polymers now will have this polyspority molecular weight, but for our simulations, we chose to use only sort of 12 mers as the chains, the same molecular weight. So it's, of course, an idealization of the real system, but that allows us to have tractability in our model. But this molecular weight is sort of close to what is used in the actual practice. So it's not that small, but certainly it's not monodispersed. Now, as I mentioned before, what they do is this random polymerization. But so we knew that in our system, given that you use these small system sizes with just a few hundred molecules, it would be very hard to really have a sample that's representative enough of a realistic random copolymer. So to really understand what was going on there, given this heterogeneity that's intrinsic to the material, I wanted to explore basically some limiting cases of this chemistry. So on the one hand, sort of the ideal scenario is you have a perfectly alternating copolymer. And that's what we're going to use and study this. But also, given that in the real system, because it's a random copolymerization, you may have some regions that are enriched in PHS and some other regions enriched in PTBMA. We also wanted to explore the homopolymers of these two materials. So if we understand the difference between these three scenarios, then that will give us a basis to understand the real system where we would be expected to find domains that look like pure homopolymer of one or the other because we're enriched in one of the two blocks, and some regions where that may look more like this ideal alternate copolymer. So as you mentioned that these are not the only three chemistries we studied also other chemistries like double copolymers, blends, but chemistries, I'm not showing them here just for conciseness. And as far as the PAC, I'm going to show you results for this sort of standard chemistry. Our simulations were performed above the glass transition temperature for these systems because we wanted to sample these quasi-equilibrium structures that would be that you would expect after the certain evaporation and annealing steps in the process. So one of the main tools that we wanted to use is this potential of mean force for salt dissociation. So the key idea is that you have this super dilute system where you have, say, only one salt molecule or two salt molecules in the polymer medium. And then you want to see how is it that the free energy of this system changes as you change the distance between these moieties. And for example, in this plot, I have the PMF, which is a free energy. And say for the single packs, you will have this corresponds to the free energy for the associated state. And this will be for the case of the dimer. So this case over here. So it will have some free energy, but if you now try to separate these moieties, for example, in the case of a single pack, you try to separate the two ions, then there will be a penalty that will manifest as an increase in the potential of mean force. And a similar thing will happen if you are trying to sort of pool two salt molecules apart. And you can continue with this calculation so that at the end, you end up with a full curve of this process up to the point where they're fully dissociated at long distances. And from here, you can extract basically this dissociation-free energy barriers, these delta G stars, as I'm going to refer to them. With the key idea that the smaller the delta G star, the smaller barrier, you will have a higher affinity and dispersibility, right? Because in some ways, this corresponds what's a penalty for you to the work that's needed to separate these two moieties. Our main hypothesis for our methodology was that the solvation behavior of paths at infinite dilution, which is this calculation, can provide a relative metric of the dispersion quality in a given polymer you have. So how homogeneously it disperses at high concentrations. Because in real life, they don't use these things at these dilute concentrations, but relatively high concentrations. But this will be the main sort of metric to quantify, to predict that solution behavior. So this shows some results for just the barriers for these delta G stars. For the case of a single path, so I'm just looking at the dissociation of anion and cation. And so what you can see is that if you were to use just the pure homopolymers, PHS has a much smaller barrier compared to PTBMA. So, and in some ways, it will be expected because PHS is more polar than PTBMA. But you can also, of course, look at the molecular structures of these systems and realize that, for example, in PHS, both the anion and the cation, which are shown below here, interact more closely with the polar groups of the OH in PHS. And even though PTBMA also has a polar group, the CO, the carbonyl group, because of the bulky terbutyl group, it's more hidden. So there's an steric hindrance, and hence it's not as effective at sort of interacting and sort of dissolving the ions. And if you look at the alternate copolymer, you see behavior in between. So the barrier to dissociation will be intermediate between the two. And when you look at some of the conformations of how the ions in the salt interact with these polymers, there is a preference of them to interact with the polar group of PHS, not so much of PTBMA. And the similar results will be seen for the case of now two salts dissociating. The values of the barriers are smaller, as you can see, but you see the similar trend where PTBMA will be the worst host for sort of dispersing this salt polymer, and hence you would expect more association in PTBMA. So these were good predictions, but we wanted to confirm them. So, and to confirm them, what that means really is that we want to also simulate the actual system. So a system where you have these salt molecules at high concentrations, order of 25, 35, 30% in weight. Because really these two things are not the same. You may wonder, well, why don't just simulate this actual system and just forget about this dilute system? Well, there are many reasons. It's true that this sort of PMF calculation is an indirect calculation. You'll have to extrapolate to the real system in some ways, and it neglects these multi-pack effects that may be important. But we felt that it captures the key driving force for the association process, poses a faster and computationally efficient calculation, and it's more reproducible and has this well-defined metric. While when you look at the high concentration system, although it's a more direct proof of reality, it's also a much more expensive calculation computationally. It's also a much more challenging for sampling representative configurations, because you may have to repeat the simulation many times to really see an ensemble of possible outcomes you can expect here. So the results are necessarily subject to a larger uncertainty, and hence could be seen as being more qualitative. But nonetheless, it would be important to do this validation and simulate these high concentrated systems. So this is what I'm going to show you now. We have to define, of course, some kind of distance threshold to decide whether the ions are close enough to be sort of clustered. And so in doing that, you can analyze, for example, what happens with these salts in the PHS homopolymer. And so what I'm showing here are the largest clusters you will see. I'm not showing you the polymer just to make things clear. And you should pay special attention to the orange cluster, which is the largest one of them. And so what our calculation shows that this large cluster is not that large in the sense that only 10% of all the salts are in that cluster. And if you look at what happens in the alternate copolymer, what you see is that now the clusters are bigger. For example, in the largest cluster, now you have about 25% of all the salts in there. And when you look at the PTBMA homopolymer, it's much worse. Now you see that you have 85% of all the salts in the largest cluster. So in this context, I will say that the scenario as a PHS, if you could just use PHS as your photoresist, that would be ideal, because I think these clusters are small enough not to bother you. Even the alternate copolymer would be potentially okay. These feature sizes are perhaps small enough to not bother you too much. But clearly, just areas of your system where you have high concentration of PTBMA will not be appropriate because it will create these large clusters and likely translate into large roughness at the end when you produce the features from this photoresist. But importantly, so our hypothesis that you can extrapolate things based on the PMF delta G star works, right? But those trends in pairwise association strength translates into this multi-body association of packs at high concentrations. Now, these observations have been further corroborated by application to other chemistries of the reference systems, just to make sure that it's not just for these three cases. Of course, that this behavior has to reflect something that's happening at the local level. And so you can look at this, basically, the solvation environment around the ions to try to understand why this happens. And what I'm showing here is basically the average coordination of an ion in the salt. And so this anion can coordinate with either the cation from the salt or from these polar groups in the two polymers. Now will be the things in blue and orange. So, and this is what you will see for the alternate copolymer, this sort of average coordination within a distance of 10 angstroms. So clearly, what you would like, and so I can show how this looks like. So with the corresponding colors, you can see what are these sort of polar groups of the polymers around this cluster of salt ions. And so what you would like is to basically reduce this brown box. They wanted to make this smaller and to make the sum of the other two larger. That's exactly what you will see if you were using just a PHS homopolymer. You see that this gray bar, now it's smaller, and the height of this is taller than the sum of these two. So this is in some ways an ideal scenario, and you can see also pictorially here how that will look like. It's sort of better surveyed. But in contrast, if you look at what happens with the pure PTBMA, when now you have these larger clusters, then what's happening is that the gray bar, so the interactions of the anion with the cation of the same salt have increased, so much at the expense of the interactions with these polar groups in the polymer. And this is really what's giving rise to this large association. So importantly, we will also see differences in the morphology of these clusters. It's more string-like in the case of PHS homopolymer, where the thickness of these strings are roughly order 1 nanometer. But by the time you go to this PTBMA homopolymer, it's a more globular aggregates, which are much thicker, order 5 nanometers. So, so clearly, scenarios where you have something approaching something like high concentration of PTBMA, like in this case on the right, will not be suitable for applications. So to conclude this part, so again, we have shown how these different chemistries have different effects on the dispersibility of the salt. Clearly, the OH groups in PHS help a lot, but not so much things related to PTBMA. And that we expect that the tandem coupling will be expected to have a behavior that's intermediate between the alternate and the homopolymers. And that our high pack concentration simulations basically confirm what we saw in the dilute simulations using the potential mean force. And so that basically tell us that in the future, we could use these PMF calculations to make relatively good predictions. And that the morphology of the structures are different. And of course, this reflects some changes in the local observation environment. And so that structure that you get there is going to be very important for what happens next, the post-exposure. And so that heterogeneity will translate also, we believe, after that. So what's left really to address is how to optimize these properties. And that's something that is still sort of work in progress. But we believe we have already this sort of a tool that would allow us to explore this question in some detail. For example, we should explore different chemistries. So I told you that it would be ideal if people could make this perfectly alternating copolymer. But that's very hard with the current ways they do this copolymers. But perhaps using other chemistries like this polypeptide chemistries would be possible, because there you can have this perfect control on the basically dispersity, the chain length of the molecule, and also what groups you attach where. So then potentially this could be a very interesting platform to optimize the photoresist. Also, the pack chemistry, and I just show you one case, but we have also exploring other chemistries that can lead to better dispersibility or worse, and trying to understand why. You can also simulate the actual thin film so that to understand whether there are some important interfacial effects between the polymer and the air that should be taken into account, because that's how the actual system looks like. And that would allow us also to compare against some experimental data that is available to understand this aggregation of the packs. And finally, we'd like to take other structures and do the sort of the post-exposure calculation that, of course, involves a lot of chemistry. All right, so with that, I want to now move to the second project, which is on engineering these dual conductor soft materials. So this corresponds a collaboration with several groups, both at Cornell, with Professor Ober, at U Chicago, Professors Neely Patel, and at Washington, Professor Luscombe. So they are in charge of doing all the experimental side of things, of the synthesis characterization. We are in charge of doing the modeling. This is part of a funded project by NSF. And the key goal is to design a single material that will be able to conduct ions, especially lithium, because that's basically the poster child for all kinds of applications, but also electrons. And for that, you will need, of course, some kind of conjugated domains. And so the uses are envisioned to be in multiple applications. And in some ways, the key idea is that this material like this will be a perfect interface to connect basically the bio world with the electronics world. You know that in biology, basically all the signals happen through ions, well, or at least most of them, while in electronics, they happen not through ions, but through electrons. So an interface that can do both would be the best way to try to interface these two signals, or kinds of signals. And in fact, it are things like this that are used, for example, in biosensors. Maybe you have seen these glucometers. So they will have to use an interface like this, but also especially it could be used in actuators. So this interface between bio and electronics, of course, and many other applications, for sure, you have ionic pumps and batteries where you have parts of the material that will require to have this dual capability. Now, we are not focused on any specific applications, just with the idea, how can you optimize a material that would be able to do both things? So again, I'm going to use the same guiding questions on what class of material to use. First, so I'm going to first make the argument that we'd like to use multi-block oligomers. And so the idea is that we have oligomers, it's the synthesis method would allow you to control better the sequence and the topology, as opposed to polymers. Usually these tend to have more stochasticity to them, they're more random. Also, oligomers are big enough to be non-volatile, non-explosive, but they're also small enough to have faster self-assembly dynamics, also a faster annealing of the effects compared to polymers. Of course, the idea of having more than one kind of chemical functionalities, because each one of them can contribute to different properties in the material. And there are, of course, many examples where people use oligomers as opposed to polymers. But there is one downside in organic oligomers, is that mechanically they're not that robust. So for practical applications, that could pose some issues. It is something that I will also address later in my talk. First, let's focus on these sort of small molecule oligomers and answer the question, what chemistry to use? Well, for the ion conducting, you will need something that's hydrophilic, right? And one of the best candidates are basically materials based on ethylene oxide, like polyethylene oxide, or PO as usually known. So that could be an ideal or a very suitable material for ion conducting. Now, for electron conducting, you need things that are conjugated, and one of the most used ones are based on thiophene. So that's going to be our initial choices. And in both cases are sort of well-studied chemistries that are safe and they are easy to work in many respects. Now for the morphology, so these two kinds of chemistries, the PO and thiophene domains, must percolate through the system, right? They have to be these channels basically that would allow you this conduction to happen of both ions and electrons, especially along the duration across the electrons. And so we thought that a laminar phase, layers that are parallel to the substrate, would be ideal or really good in some ways, because, for example, there are simple techniques that will allow you to functionalize the substrate so that basically one of the blocks or one of the chemistries would like to be down there, and if the system wants to form a lamellar phase, you have this sort of nice registry of the lamellars that will be with layers parallel to the substrate. And then you have this conduction that will go, say, from left to right or vice versa. And so we came up with the idea of synthesizing or studying the system that, as you can see, is like a small tri-block. So in the middle, you have these hydrophobic pi-conjugated rings of thiophene. In this case, we have 4 of them. And on the sides, we have these short chains of PO. So in fact, we use basically 4 ethylene units on either side and 4 thiophene units in the middle, with the expectation that they will form something like a lamellar phase, and we can have these different domains for different kinds of conduction. So as far as the salt I will be using for the ion conduction, also known as the ionic dopant. So for sure, we want to use lithium as a cation. For the anion, there are a number of choices, but the one that is used a lot. And initially, we didn't understand why, but now we do, and I can explain that if anybody has a question. Is this sort of more bulky and complex molecule that I'm just going to refer to as PFSI. So then with these choices, we then proceed to basically use some of our experimental and modeling strategies to try to understand. Now, I should focus that we're only going to talk about ion conductivity, not the electron conductivity, in part because we have studied that much less, and second, because that's in some ways a bit more understood in some parts of the literature. So we wanted to focus on this sort of important gap in understanding ionic conductivity in these materials. So our collaborators synthesized, prepared these substrates, and then characterized them in different ways using microscopy, using thermal calorimetry, and of course using X-rays to try to understand what is the structure that you get in this substrate. This illustrating sort of a two-dimensional X-ray spectra. So this QR will be basically the lateral signals, and the QZ will be sort of vertical in these layers. Now, as far as the modeling, we thought that, well, seems like a simple enough chemistry. We can use an atomistic model to simulate this, but it turns out that the atomistic model wouldn't assemble into this lamellar phase. It was taking a long time, and it was very, very sluggish. So what we decided was to first cross-grain the atomistic system so that we can have sort of a faster simulation. So then this coarse grain simulation was able to assemble into this expected lamellar phase in a reasonable time and investment of computer resources. And the idea is that, so once it assembles into the right structure, then we can sort of use that as a template to basically cast the atomistic model into this structure, and then use a simulation, of course, and annealing to fully equilibrate the atomistic system. So that's what we did. That's why we ended up with a structure that looks something like this. So once you have the structure, of course, you can also analyze it using a simulated X-ray pattern. And then you can compare the experimental with the simulation patterns to make sense of these diffraction peaks. For example, the diffraction peaks here shown as 001, 002, and so forth, they reflect basically the layering structure of the material that was expected. So we know it's some sort of lamellar phase. But for some of the A and B peaks, were a little bit more pulsing. So, but the analysis showed that they basically correspond to some sort of periodic distance that happened in the system, reflecting the packing of the thiophene pores in the material. So in the figure up here, the thiophene regions are in blue, and the PO regions are in red. And so what basically that demonstrates is that these thiophenes are packing in the same way how thiophene will pack in its crystalline state. So that's basically telling us then that you have something like a solid when you come to the packing of the thiophene cores, while you have something that's much more amorphous, kind of liquid-like when it comes to the structure of the PO chains. Now this seems strange because now that you have this structure, is this a solid? Is this a liquid? So we decide to call it a liquid crystal, even though that denomination may be a bit misleading. But it's really a very interesting structure if you think about it. We have this, so layers which are really thin, or the 2 nanometers, but you have this intercollection of solid, liquid, solid, liquid, solid, liquid. So I think that alone makes it a very fascinating material. But importantly, this different kinds of structures are ideal because if you want to conduct electrons, you want to have a solid, an ordered material, right? Because the electrons are going to go through these conjugated pi states, and you want them to be sort of in some particular positions. While if you want the conduction of ions, you want it to be in a sort of liquid-like state because the ion actually has to move through these different layers. So in some ways, it was an ideal structure. And when our collaborators characterized the system by this sort of electrical test to see ionic conductivity and electron conductivity, they found that it was an excellent Duan conductor. In fact, comparable or even better than the best one that has been reported in the literature. So we felt that, wow, we were at a very, very promising start by having chosen that initial chemistry, but of course we wanted to go beyond that and potentially optimize this. So this is just to show you that there's a temperature range of operation. If you go too high, then the system is going to melt, and then you no longer have this sort of herringbone structure for the thiophene rings. Now, as far as the methods, if you want to probe ionic mobility and conductivity, so typically we will have to use an electric field, so we apply an electric field to be able to sort of see the motion of these ions in some reasonable time, and then you will track the motion of the ions through the system, through this polymer. And you can characterize that mobility by using the mean square displacement, this MSD, as a function of time, or here as a function of time squared. So the more it moves, of course, the larger these changes will be, and also that may be reflected in the slope. You can apply Ohm's law that basically relates the drift velocity Vx with the applied electric field to be able to extract basically what's this drift velocity. And then that can be extracted from these plots of this mean square displacements. So in the simulation, you can extract this drift velocity that way. And the formula for the conductivity is as follows. So it basically says that it's proportional to the ionic charge, of course, is proportional to this drift velocity, and is proportional to n, which is basically the number of these dissociated ions you will have in the system. But it's inversely proportional to delta G star, which is this dissociation free energy barriers. It's basically the same delta G star that I talked to you before for the other system of photoresists by using this PMF calculation. So clearly you need to have all these elements, and of course they will be applied to the dissociation of lithium with the TFSI. And this kind of calculation can be used in many situations, but mostly we use it to prove the behavior at infinite dilution of the lithium. So assuming that's in a fully dissociated state. Now, this formula already provides a lot of sort of insights as to sort of a rational strategy to try to design these materials. For example, you will try to choose a salt organic host pair such that the salt dissociates easily, right? So you want this delta G to be as small as possible. Also, the more dissociated, for a given concentration of salt, you will have a larger number of dissociated ions, which is what you need for this little n in there. So clearly, that choice is going to be important. We can use similar ideas as before, that you can explore different chemistries and try to identify the ones with the smaller delta G star as suitable candidates for this. Now, as far as the effect of salt concentration, that is usually quantified by this number R, which is a ratio of number of lithium ions relative to the number of oxygens in the ethylene oxide units. What happens is that initially, as you increase R, the ion conductivity also increases, which makes sense because you are increasing the number of charges. So in some ways, you are increasing the N in this formula. But only up to a point. By the time when you keep increasing this R, the conductivity starts decreasing. And the reason is that some of those additional ions just stay associated, so they don't contribute to ion conductivity. And many of them start basically cross-linking with the oxygens in the ethylene oxide units. So basically, they are gelling the material and they are reducing the segmental mobility that would be important enough for these ions to move through this layer. So there is an optimal there, which usually happens around R of 0.05 to 0.1. Which is something has been found experimentally and also simulations supporting some of these observations. So, what are the mechanisms by what this conductivity happens in these materials? So the key observation is that the lithium ion tends to be associated with the oxygens in the ethylene oxide units. That's been known for a long time. And then the mobility or the motion then can happen by co-diffusion. That's where the cation and the molecule which it's associated move together. Right? That tends to be more gradual, but also via hops, where this, say, the ion basically moves from either between two molecules or between two regions, different regions within the same molecule. So these hops will be in some ways more drastic than co-diffusion. And co-diffusion will be in some way depending on the whole molecule to move, that can be too slow. So for sure, the signs that favor hops would be beneficial. And in that context, the abundance of chain ends would be favorable because they are more mobile than sort of segments which are inside the molecules. And also they will promote hops because if you go from one chain end to another chain end, that will basically make it more effective. So and that basically tells you what the effect of the lateral chain length is. So besides modulating the melting point of the material, so we'll basically define what's the rate of temperatures where the material can be worked on. They didn't want it to be, they want to be operating things, say, above 100 degrees Celsius or below room temperature. But more importantly, it basically controls the concentration of chain ends, right? So in that sense, it would be preferable if you have a system where you have basically short PO side chains. And in fact, that's exactly what we had in this liquid crystal that I showed you before, with 4 thiophene and this PO material. So the next, we wanted to address this question that I told you before, that the issue with these small molecule systems is that they are not mechanically robust. So in applications, you need to basically address that. There are at least 3 possible ways you can try to improve that. So one will be by, okay, you form first the layers and then you try to cross-link them, right? So this is something that we're exploring with our collaborators. Of course, needs new chemistry for the end group so that they can react upon some activation. So the second is that what if you premix some additives into the system that may actually serve to couple multiple layers? This is the idea of using sort of stapling or staples to do this, and I will mention this in a moment. So the third will be, well, just make them into polymers. I will also talk about this approach. So for the second, so the idea is the following. So imagine that you have two sheets of paper, one on top of the other. And if I were to apply a shearing force, then you expect that, well, just there's not enough adhesion between these layers, so they are just going to slide one past another. But if you were to staple them, right, something basically couples these two layers, then the shear force will be ineffective in deforming the system that way. And that was basically the idea that we wanted to introduce for the material that I showed you before, this sort of small treadlock. That the structure you form, this laminar phase, has basically these regions in red, where you have the PO segments, that are more mobile, so they're not sticking to each other very strongly. While the regions where the thiophene are, here shown in blue, these are more solid-like, so they're much more robust. So the weak point basically is really in these red regions. So if you were to add a molecule that was longer, like this sort of pentablock, that would allow you to basically connect these two blue domains, then effectively you have produced something that would be mechanically stronger. Of course, that if you put this staple into the system, you wouldn't necessarily expect that the molecule will go sort of stretch like this. You can also have these loop conformations. So the one on the rightmost figure will be ineffective in really promoting this coupling between the layers. But according to our calculations, you can expect that at least 38% of the chains will have this bridging conformation and will be effective in doing this stapling of the layers. So these are just some preliminary simulations showing that indeed, if you add staples to the system, you can improve the stress response to strain and basically improve this sort of shear modulus of the material. Although these simulations are not the best for capturing really the solid-like structure of the thiophene pores, because these are coarse-grained simulations. So what we are doing now is basically atomistic simulation to get a more sort of precise signal for this. But in doing this exploration, we came up with the following thought. Well, why not just use a system with pure staples, right? So basically, rather than using these little triblocks, let's just use something a little bit longer with these pentablocks. And at least for simulations with this coarse-grained system show that indeed the system will still assemble into the lamellar phase, and you will have this high chance of having this interlocking between layers, because at least 30% of the chains will have this stretch conformation in doing that. So we're still trying to convince our collaborators to synthesize it and give it a try. Apparently, it's not as simple as what they did before for the triblock, but this is still a work in progress. So finally, I want to talk about sort of also improving the functionality. So not just the mechanical properties, but also the functionality. And to do that, I'm going to basically consider the use of polymers. So we want to have something that's strong, the true material, but let's just use polymers. But in such a way that you also have a high concentration of PO chain ends, because as I told you, that's important. And so we choose with a system that will look something like this. Basically, it's a pegylated thiophene polymer. So the monomer will look something like this. And this is inspired in a material that's well known, known as a P3HT. That's a non-organic photovoltaic material that basically has this thiophene cores the same, but you have this side chain which is just alkylated. So this system will not, it's good at conducting electrons, but not at conducting ions. So to conduct ions, we change the alkyl chain by basically this PO side chain. Now, so this system, just like P3HT, is expected to form this crystalline phase that looks something like this. You see that the thiophene rings will tend to basically crystallize into these planes, while the side chains will form this bilayer structure. Now, it shouldn't escape your eye that these bilayer regions of PO are very similar to basically the layers of PO that we had in the liquid crystal oligomer that we studied before. So in that sense, many of the lessons will be transferable to the other system as well. Now, the problem with the polymer, for different reasons, this system relax more slowly, and they are prone to kinetic traps, and you have more polydispersity, that you don't just get this crystalline state, but you also get an amorphous state. In fact, our best understanding is that what you form is really a semi-crystalline material. We have these domains of crystallites embedded in some kind of matrix of amorphous material. So that complicates a lot the characterization and the interpretation of results from experiments, but also from simulations. So we did not attempt to model something that contains both, but basically study systems which are either 100% crystal or 100% amorphous, and trying to learn lessons from there to then try to sort of extrapolate to what will happen if you have sort of mixtures of both. So it's important also to understand sort of the local structure of these materials. So again, this is the material we're simulating with this polymer, and it's the same salt as before, lithium TFSI. Now, typically in this, when the lithium salt is in this sort of regulated environment, is going to be coordinated with 6 oxygens. So the oxygens that come from this side chain in the sorbation shells around a certain distance of basically the first sorbation shell of lithium ion. And if you look at the PMF, so basically what happens when you try to dissociate the 2 ions as a function of their distance. So the curves are very interesting. They look something like this. You can see it has multiple peaks. So this region will correspond to association, and this region will be dissociated. And so the curve is the PMF. You can also see the barrier will be the difference between the bottom and the top. But what's shown on this other scale on the right and with the colors is basically the kind of atom that's being associated with the lithium. So I said it's a 6 typically, and that's what you see this upper bound. You can see that goes up to 6. So that's basically all the oxygens that are coordinated with it. But you can see here in this sort of purple color down here that there will be the association of oxygens not with the oxygens in the PO, but the oxygens in the anion. So you see that the TFSI anion contains a number of oxygens, and they also tend to associate with the lithium. So you can see that initially they have significant association, of course, with the anion that later goes away as you separate the 2. But so these different minima are very meaningful because they are telling you that there are some sort of metastable states, right? So the first minima 1 corresponds to the moment where the lithium ion, which is shown here by this sort of whitish bit, this larger bit here, so has 6 oxygens coordinating, but 2 of them are coming from the anion. So these 2 down here, they are important. And that corresponds to the minimum. So what happens in the minimum 2 is when you break off one of those 2 oxygen coordinations with the anion. So now you have this structure. And then when you break off completely this association with the 2 oxygens and the anion, then you have this state 3. So clearly to go from one to the other, you have to go through these little barriers, right? That at the end amount to the total barrier to dissociation. So with the main barrier is the one between stage 2 and 3. And after that, we will have these other features in the PMF corresponding to basically changes in the sorbation environment. And of course, these results are for the amorphous phase. You can do a similar analysis also for the crystalline phase. You can be even more ambitious and look at not just the oxygens that come from the PO chain, which are coordinating with this lithium ion, but also identify which oxygen, whether it's the one closest to it, which is number 1, or the farthest to it, which is number 3. And all of these things will give you some insights into this local environment of sorbation shells. But importantly, we want to understand the ion conductivity, of course. So these results are going to be for a value of concentration of ions of 0.05. We're going to look at the crystalline and the amorphous system. And if you look at this mean square displacement of the lithium ions, you find that it actually travels much faster in the amorphous material than in the crystalline material. If you look at the anion, the TFSI, you see that they are more comparable, but in this case, it travels faster in the crystalline region than the amorphous region. But importantly, if you compare the vertical scales of this mean square displacement, it shows that TFSI moves much faster than lithium ion. So in terms of just the raw total ionic conductivity, the anion contributes more than the cation. But for many practical applications, you care more about the motion of the lithium itself, because that's the active material that maybe you want to move from here to there. So you need to pay attention to the lithium mobility and also the total conductivity. Now, this gave us the idea that so maybe what we need to do is sort of modify this observation shell around these ions to see whether that may help us. For example, what if you were to reduce the number of oxygens in the side chain of this PO chain? That may actually help us modulate the channels through which these ions are going to move. So then we explored changing the number of oxygens in this side chain from 3, that gives you a ratio of basically 3 to 9. This is the ratio with respect to the total number of heavy atoms. You can have, for example, variants where you have only 2 oxygens, not 3. And you can put the 2 oxygens in different points along the chain. Or you can have only 1 oxygen, where that again can be in different places in the same chain. And in fact, experimentally, they synthesized 5 of these systems, so that it allows us to have comparisons with simulation methods. And so this will lead results for the crystalline material. And here I'm just showing this is what you would expect, and we find in the case when you have this sort of 3 oxygens, that will be the normal PO side chain. And so here showing the atoms in different colors. But if I were to highlight the regions which are pervaded by the oxygen, just in the middle by layers, so right here, you see that basically the whole layer is permeated by oxygens. Well, if I were to do the same thing for the other chemistries, so you see that these red regions are smaller and sort of more, so less connected. And if I were to ask you, just based on these diagrams, which material would seem to be the best at solvating the salt? Probably most of you will say the first one, right? Because you have a larger region of oxygen, so it should be easier for these ions to find this interaction with oxygens to dissociate it. And you will be right. We look at basically these free energy barriers for these different materials. The smallest one corresponds to this chemistry, which is the standard PO with the 3 oxygens. And the barriers become larger once you have smaller permeated regions by oxygen groups. So that in some ways was to be expected. But if now you look at the actual ionic conductivity, which is sort of normalized so that 1 corresponds to the base system, which is the first one, what you find is that sort of more nuanced. Now, in this case, you find that, in fact, the second system, so basically the one here that has only 2 oxygens near the chain end, was in fact somewhat better than the base system. And so one reason that we came to understand is that the oxygen which is too close to the tyrosine ring is the less mobile of them. So if the lithium ion tends to be associated with that oxygen, in some ways that's going to slow it down somewhat. So at the end, even though that system has a slightly higher barrier, so it's harder to dissociate, and when it comes to the mean square displacement, it tends to move better than in the system, so the canonical system. So that was interesting. Now the results for the amorphous system are somewhat different. For some of these systems here will have smaller conductivity. So, but at the end, this analysis concluded that yes, you can improve slightly from the base system, the pure PO, but not a whole lot. So then we ask the opposite question. So what now if we actually increase the concentration of oxygens, perhaps to reduce the Hopf length? And you can do that because this is the base chemistry again that we used before, and you can actually use other chemistries where the ratio of oxygen to number of heavy atoms can be increased up to 50%, like in the last system over here. So in that case, if you do that, expectedly you will find that the barrier to dissociation becomes smaller. And if you see these curves, you see that the larger barrier corresponds to the first system, the PO, and you can make it smaller. The more oxygen basically you have in the smaller barrier, and which makes sense because you have a more polar environment. And if you see the mean square displacement of lithium. Again, you see that the one with more oxygen tends to have faster mobility, and the same thing for the anion. So clearly, one of these systems should be better at this role of conductivity of lithium ions. But again, we're in the situation where the predictions are a bit too way ahead of the experiments by our collaborators. But so we hope that we will be able to report about some of these experimental systems in the future. So with that, I'd like to just conclude based on the same guiding questions I showed before. So the first two is basically just the reasons why we chose the materials we want to study, the tools that we use to try to understand and characterize the systems, and that to optimize the functionality. So we want to have more ionic jumps, which are favored by a more abundance of oxygen, but especially near the chain ends, that the shear modulus of these small liquid crystalline materials could be improved by staples, for example. But importantly, that there are these translational entropic effects that explain why when you have a more disordered liquid crystalline system or amorphous polymer, you have actually improved ion conductivity. So we're also exploring other chemistries, beyond the thiophene, these oxygens in ethylene oxide, and on the anion for the salt. So with that, I'd like to acknowledge basically the two main students that work on this project, Prajoao for the first one, and Yang San for the second one, and also acknowledge the funding agencies that help us and some of our collaborators. So thanks a lot for your attention. I'll be happy to take any questions.
Thank you, Professor Escobedo, for the presentation. We are now open to questions. If you want to participate, please enable your microphone or write it down in the chat. Also, our YouTube viewers can write it down too, of course.
Let I ask something.
Sure.
Professor.
Thank you, Fernando, for your talk. These results are amazing, very, very interesting results. Let I ask you, the first study is about how about use the PMF instead of use PMF, how about use coarse grain model for a large system instead of a small sample for your system? Maybe if you do coarse grain, you could do much larger sample, and this for the first part of your talk.
Yes. Yeah, no, that's a good point. And at some point we had thought about doing that. And I mean, one reason why we wanted to use coarse grain systems for this material is to be able to understand better the structure at the mesoscale, right? So how is it that they form initially, but to really understand these interactions, you really have, it's really all about what these ions experience, right? And so the details of a local environment seem to be very important, what kind of partial charges you assign to different groups. So we felt that if you coarse grain the system, you're going to lose too much detail to really capture this information. So I think that coarse graining would be good in the sense of helping you create initial general structures, but to understand this dissociation or association behavior, that it was important to use this atomistic system. And I would say that after the fact, these systems are more expensive, but they're still, I think, manageable. They're not overly too expensive. That, of course, the system size is limited because of this. But yeah, so I think that we thought that it was needed to do atomistic system for this. Believe me, I am a person that I love to use coarse grain models, but we felt that in this case, you need to go in more detail. And in fact, for some things, we need to use actually quantum mechanics, we use density function theory to understand better whether it was, for example, some of these partial charges that were being assigned to some of these groups made sense.
Whether some of these molecules are polarizable, and this maybe change the. I see.
Yes.
I see.
Yes. Yes.
Thank you. Another point is about the second part that you have shown us. Uh, I think what's very interesting to see the mobility effect for the liquid-like phase in your polymer. But I was thinking about the smaller the anion maybe is better, but you have shown some result that shows exactly the other way around.
Yes. So if I can show you quickly, yes. And I have the same question that, so when you consider the salt, right? So as I mentioned, you want lithium as a cation, but as far as the anion, you think that something smaller would be better, right? And initially, so why not just a chlorine anion, right? Like is the one shown here. And in practice, people have used different kinds of anions. The one that seems to be most popular now, works really well experimentally, is this TFSI, which is in some ways the bigger one in this series of anions. Now, when you do the PMF calculation, interestingly, you find that the lithium chloride is the one that has this strong dissociation barrier. So the two guys are associated too strongly that that's going to be not beneficial for this ion conductivity. So in so much you want an ion that is not bound to the lithium too strongly. And all of these guys over here do more or less that. You see that we have these smaller energy barriers. And so it's amplifying here that to see that there are some slightly better than others, but on the whole part, they're somewhat similar. Now, if you now look at the mean square displacement so both you can look at how the lithium moves in the this is in the simulations in the crystalline phase, these later structures, and seeing how things move in the PO region. You see that the lithium moves much faster in the TFSI when you have this TFSI ion compared to the other ones. The anion itself, there's some differences. So this PF6 seems to be slightly better than TFSI. But as I said, sometimes people care more about the mobility of lithium ions. So in that context, the TFSI will be the best. And so it's interesting because I guess it's designed in such a way that one is not strongly bound to the lithium ions, and yet they have enough oxygens in there to solvate it well, so you have a large barrier for dissociation. But also this moiety, if you think about it, is somewhat like an amphiphilic material, right? You have these CF3s that are hydrophobic. So because of that, then the system doesn't necessarily stick around long, and it's able to sort of move more easily. You just need a small bias, and this molecule is going to move despite being bulky. So I found it fascinating because, again, initially we didn't understand why this would be the anion of choice. I would think that something smaller would be better, but at least.
Do you think there is anything related with maybe a plasticity of this local phase?
Yes, exactly. That's a good point. That because of the bulkiness of these groups, basically makes this disordered phase of the PO regions more disordered, right? So that's what I was saying. These entropic effects that counterintuitively, that if you introduce more disorder, that is going to sort of affect these ion conducting regions. That's going to basically favor the mobility of the ions in there. So certainly there's an effect in there too.
Really fascinating effect. It's amazing. Yeah, I think that's it, my questions.
Thanks a lot. That is very good questions. Thank you.
Thank you for presentation. It's very nice.
You're very welcome.
So does anyone want to add another question?
I think it's time, yeah?
Okay, so our time is almost over. We want to thank everyone for this discussion. And once again, thank you, Professor Escobedo, for the presentation.
Great. No, thank you for the invitation. And so if somebody has any questions, you can always email me, of course. Thanks a lot for the invitation, for your attendance.
It's our pleasure. So our seminar, please, Professor.
Well, Thanksgiving for you, Escobedo.
Excuse me?
Well, Thanksgiving for you.
Oh, thank you.
Yeah.
Thanks a lot. Yeah. And I'm looking forward to the game with Brazil in the soccer.
Sure.
Yeah.
I hope no surprise, yeah?
I hope so. Yeah. Yes. Yes. Yes.
Okay, so our seminars are being recorded and posted on YouTube after the Invictor Lectures Agreement. And please check them out on our YouTube channel.
Just a moment, João.
Oh, sure.
Professor Escobedo, can you please unshare your screen, please?
Okay.
Thank you very much.
Sure.
Okay, and sorry, I think the audio is doubled. Thanks. So please check them out on our YouTube channel. And this is our organization committee. We are responsible for inviting and communicating with the lecturers. We also handle social media, certificate writings, and hosting. This was our last seminar of this year's series, so we'll meet again only in 2023 in our new and rebranded format. So now we're going to briefly watch our teaser for our new seminar series.
What I would like to talk about today is it's maybe slightly different.
Science is always evolving.
Molecular dynamics, DFT calculations, machine learning methods, electronic transport calculations.
It's hard to keep up.
I don't think that's been studied.
But in the field of thermodynamics, you can find it all in one place.
That's very interesting. I like that.
The Atom Seminar Series brings the newest topics to you.
Quantum chemistry, molecular simulation, statistical mechanics, classical thermodynamics.
Worldwide known researchers.
At least for engineering applications, I would like a water model that can represent ideally
insights about the future.
The question is, do you think other substances would also turn metallic if they were at high pressures?
Open questions.
Let I ask you something.
In 2023, we invite you to be with us in a brand new format.
Okay, guys, so that's all. Thank you all for being here today and for participating in our seminar during all this year of 2022. And see you all again next year.